Hi everybody, Greg McCaskill with Rohde & Schwartz here. Welcome to today's webinar. We're going to be talking about the 6 things your next oscilloscope needs to have. We'll touch on the terms that we're going to cover in the webinar, and then we'll dive right in with a presentation that's broken up between presentation and demo at each stage. We'll be talking about some of these key benefits that come from the features of the MX-04 and show you how those benefit you if you had one of these scopes on your lab bench. And at the end, of course, we've got a Q&A, and I'd love to go over your questions. So what are the key terms we're going to talk about when we talk about the 6 things your next scope needs? Here they are. Of course, with scopes, we talk about update rate and noise and memory, etc. But in this case, we're going to say that you really need to have a fast update rate, low noise, deep memory, a digital trigger. We'll talk about what that is. A superior spectrum capability, or FFT, and the Rohde & Schwartz Smart Grid, which is our user interface. And we're going to go over why we think you're going to want these and need these in your next scope. So first is fast update rate. So what's update rate? We're really talking about acquisition rate here, and in the graph on the bottom and the image on the bottom, you can see the total acquisition time is composed of an acquisition and blind time. So an acquisition rate is how quickly the scope can trigger, process, and display sequential waveforms. It's specified in waveforms per second, and of course the higher the better. It's also called update rate and capture rate. And the smaller the blind time, the faster your acquisition rate will be. So one of the goals is to shorten blind time, to get more waveforms per second. So what are the elements of acquisition time? Blind time is the biggest component, and it has a fixed component and it has variable components. Variable blind time is a function of record length, the number and types of post-processing you're doing, the time required for displaying. And update rate can also be limited by user settings. For example, if you're going to capture 1 second's worth of time, then you're only going to be able to update as often as once per second. How can a higher acquisition rate reduce your test time? First of all, it's going to give you better signal visibility. Second thing it's going to do is increase the statistical probability that you're going to capture your rare events. So with that increased probability, you're going to capture things quicker. Next, the responsiveness of the scope is going to be better. So you're going to be more productive. And finally, the fourth one is statistical confidence. Why is this? Because you're going to be acquiring data more rapidly. So you're going to get to more statistical confidence quicker. So let's take a look at a demo of fast update rate. And for that, I'm going to switch to the scope. Here I've connected to an MX-04 through a web browser. This is one of the techniques for graphically interacting with an MX-04. Of course, it looks a little more lively in person. I'm connecting over LAN here, but this is a nice way to show you the scope virtually. The side panel has sections for trigger, horizontal, vertical, and a multi-use section with things like an app button. And in that app section, I'm going to access the demo menu and show you the key benefits demo. And for the purposes of this demo, I'm going to turn off the side panel so we can focus on the screen. So I'm going to show you 2 ways of thinking about fast update rate. The first is if you have a signal that you know has glitches or you believe has glitches, the faster your update rate, the quicker you're going to get to see those rare events. And if your update rate is slow, you might never see them because your statistical chance of seeing them is incredibly low the slower your update rate. So in this case, we're capturing about 100 waveforms per second, and there's a glitch once per second, and we're not seeing it pop up at all. If we eliminate that restriction and run at the full performance of the MX-04, you'll start to see that glitch pop up from time to time. There was a runt, there's another runt, and I can show you in the acquisition menu the speed that we're currently running at. So in this case, we're running at over 3 million waveforms per second, and we're capturing greater than 60% of time. So most scopes in this class are going to be about capturing around 1% time and be primarily blind. So this is a significant improvement over other scopes in this class. So see rare events quickly. The other way of thinking about fast update rate is if you have a dynamic signal and you want to see the real behavior of that signal. In this case, we have a signal that appears to be AM modulated, and you're definitely able to see that that's happening here. But if we show the full update rate of the MXO, you can clearly see the full behavior of that signal. So fast update rate also lets you see the dynamic nature of signals. Perfect. Switch back to the presentation. The second benefit we want to talk about, the second thing your next oscilloscope needs to have, is low noise. So what does low noise do for you? It enables you to see small signal details. And where do you look to in an oscilloscope to reduce noise? Well, you look to the front end, the analog components, and that's composed of an analog filter, a variable gain amplifier. Those are the two primarily analog components, and then you have the ADC. And so the ADC is one of the elements that we're going to focus on here. Obviously, you need to do the best job you can on the variable gain amplifier and the analog filter, but usually this analog to digital converter is purchased from another company, and you want it to have a large number of bits, and you want it to be low noise. So let's talk about that a little bit more. So the smallest voltage difference that an oscilloscope can measure is the vertical resolution. And as you increase the number of ADC bits, you increase the vertical resolution. For example, if you had an 8-bit scope, there would be 256 quantization levels. And so if you were looking at 1 volt peak to peak, the best you could measure in a delta voltage would be 3.9 millivolts. If you instead had a 10-bit ADC with the same scope settings, you'd be able to measure 1 millivolt. So that increased resolution lowers the noise in this way. So the key advantage, lowering noise, that allows you to see smaller signals. It also increases your dynamic range and gives you better measurement repeatability. So what are some ways of improving vertical resolution? Obviously, you can buy an ADC that has more bits. You can also do averaging. There is a trade-off related to averaging, and that is that it requires repetitive signal. You could use high-resolution mode, or what's frequently called high-res mode. It has a couple of trade-offs. One of them is sample rate, and the other is bandwidth. And with high-res mode, it's not always obvious how much bandwidth you're trading off. So you have to use that one with care and spend some time thinking about the settings. Excuse me. And the fourth is high definition mode. And this one also has a trade-off with bandwidth, but it's a little more clear. You know exactly what bandwidth you're trading off to achieve a resolution. And so if you know the behavior of your signal, you know what bandwidth is acceptable. So how does HD mode work? This is a low-pass filter that's placed after the ADC. Excuse me. And it can enable you to achieve up to 18 bits of vertical resolution. It's implemented in hardware and an ASIC by Rohde & Schwarz, and it improves your signal-noise ratio and vertical resolution and decreases noise. There are 4 main benefits. It does not require a repetitive signal, so you can do this in single-shot mode. It does not reduce sampling rate. It does not slow down processing since it's done in hardware. And the digital trigger also sees this signal. So you have an even better, cleaner signal for the trigger to see. So going back to this signal that we looked at right at the beginning of this section, here, because of the number of bits, we're not able to resolve the fine detail on this signal. If we enable high resolution mode, or HD mode, I'm sorry, then you're able to resolve this signal because you've increased the number of quantization levels. And also I touched on digital triggering. That also enables you to do things like trigger on that very small edge right there, and we'll look at an example of how that works. Okay, perfect. So let's look at a benefit of low noise. And the first way we're going to look at this is to decrease the volts per division all the way down to 500 microvolts per division, which is the lowest setting of the MX-04. And we've got it set up in 50 ohms. And we've also done an FFT all the way out to 1.2 gigahertz. This particular MXO is a 1 gigahertz unit. And we can see in the time domain trace that even at 500 microvolts per division, there's very little noise riding on that trace. There's nothing connected to the front end, and this is really low noise. In the frequency domain, we can see that the signal is down around minus 95 dBm. It's flat. The FFT is flat. There are no spurs. And it's flat all the way out to the full bandwidth of the scope and beyond. So really low noise. Another way of looking at low noise would be to show that signal. And here's that large sine wave, and it's got some signal superimposed on top of it. And here's the zoom window showing the top of that sine wave. And we can see that something's definitely happening. We're in 12-bit mode, but we're not able to resolve that. So if I press run single, for example, you can see that something's happening, but the quantization levels aren't fine enough to resolve the finer details. So if we turn on HD mode and do another run single, we're going to see that the scope is easily able to resolve that small signal. And if we take a look back here at the acquisition, we're now in 18-bit mode. And so that's the benefit of having a low noise front end that includes that variable gain amplifier and analog filter, plus a lot of bits in HD mode. Next, let's talk about deep memory. And the main thing that deep memory allows you to do is capture more time. You might be thinking, okay, well, my scope's got a time-based knob on it. I can crank that as far out as I want to go. And the truth is, yeah, you can crank that out and capture more and more time. But at a certain point, your scope's going to run out of memory. And as you run out of memory, the sample rate is going to go down every time you increase the time base. So you will be sacrificing the quality of your captured signal. The edges won't be as clean, and you're going to start to alias and things like that. So we say that more memory allows you to capture more time, and that's because it allows you to capture more time at a high sample rate. So here's an example of that. We have a 400 microsecond capture, and then two different zoom windows. The zoom window on the left is when we only had a megapoint of memory, and you can see that the signal looks distorted and it varies. And then the signal with 800 megapoints of memory, we can see it looks much different. The edges are sharp, the signal's consistent. So if you were taking a long capture and you had 1 megapoint of memory, your rise times and things like that are going to be inaccurate. And if you were decoding some type of low-speed serial standard, you'd probably get inaccurate results. So memory allowing you to capture more time. Another way to think about memory is let's assume that this bursted signal is something we want to capture. If we have a limited amount of memory, this blue box represents what we might be able to see. So we'd only be able to see maybe one capture. And you might be thinking, okay, but my scopes typically have segmented memory, and that's always been a nice feature, and that enables you to just capture changes in behavior, so you can ignore this dead time. More memory is still going to benefit you because you're going to be able to capture even more segments. So that's an additional benefit of having deep memory. So let's take a look at the demo of deep memory. So here we have a 2-second long capture, and I'm allowing the scope to use about 32 megapoints of memory, which is quite a bit of memory. And it's a square wave, but it looks like there's a lot of ringing, which tells me it's not sampled enough, and the edges don't look that sharp. I mean, by that I mean not very steep. And so if I was taking this long acquisition and I was wanting to perform rise time measurements or other measurements, the accuracy of those measurements is not going to be very high because this appears to be undersampled. So let's change that from 32 million points to the max memory of the scope, which is 800 megapoints. In this case, it's using about 770 megapoints for this particular setup and capture. And now you can see the edges are clean, the ringing is gone. So we could take a very long capture and still have confidence in our measurements. Perfect. So moving on to number 4, which is digital trigger. What is a digital trigger? Well, first of all, let's talk about trigger sensitivity. And what we're looking for in a trigger usually is a rising edge. This is the most common trigger, would be an edge trigger. And let's say we're wanting to trigger on every edge that comes through. So here's a rising edge, and it's crossing the trigger threshold, but it has to actually cross through the entire sensitivity of the trigger. It's an analog circuit, so it has some amount of sensitivity. It needs to see a certain level of voltage swing, but it does achieve that, and the scope triggers on this pulse. What about the second pulse? It crosses the trigger threshold, but the signal voltage swing does not pass all the way through the trigger sensitivity level. So this pulse would not trigger the scope, and you wouldn't capture it. If you're able to reduce that trigger sensitivity to an incredibly low value, where it's basically non-existent, then you're able to trigger on both of these rising edges. And that's what a digital trigger enables you to do. How does that work? Let's take a little bit deeper dive into these two trigger systems. So first, an analog trigger. There's a path that splits off before the analog to digital converter that goes to the analog trigger circuit. And the signal is going to be observed by that analog trigger circuit. It's going to have the trigger level, and there is going to be some amount of trigger sensitivity, and that might be half a division, it might be more than half a division, but there's some amount of trigger sensitivity. It's in the data sheet for oscilloscopes, but that has to be met for a trigger event to occur. Meanwhile, the ADC samples the acquisition and processes that, etc. But if a trigger event doesn't happen, then that acquisition is thrown out. Digital trigger, on the other hand, is a hardware block that's right after the ADC. So the digital trigger actually uses the sampled waveform. And so that means it can trigger on a sensitivity just greater than the ADC resolution. And keep in mind that HD mode is before the digital trigger, so even that finer resolution that HD mode provides, the digital trigger can see that. So basically, if you can see it on your scope, the digital trigger can trigger on it. let's take a look at what a digital trigger looks like. So here is a capture that has these pulses that increase in amplitude. The scope is actively acquiring, and I'm moving the trigger level up and down so you can see where that is. In this case, the trigger hysteresis is basically set to 0, so very fine hysteresis, and I'm triggering on this big pulse. This second pulse, if I brought the trigger level down, you can see that now we're triggering on that pulse. But think about if your trigger sensitivity was half a division or more, you may or may not be able to consistently trigger on even this pulse. And because your overall signal has small elements and big elements, you can't make this signal any bigger on your screen to try and capture it. So you're really limited here by your trigger sensitivity, but not with a digital trigger. And you're certainly not going to be able to scroll down and trigger on that next signal. In this case, I've turned on HD mode, and you can see that the signal is cleaner, it's more defined, and I'm triggering on that very small pulse right there, which would clearly be impossible on an analog trigger. So I'm able to trigger on small signal details even when my overall capture has much bigger voltage swings. If you want to take a look at something even finer, let's say we want to trigger on this rising edge that's down on this undershoot of this signal. So right now, this is my trigger point right here. And you can see up here in this view is this very small detail of a signal. So again, a digital trigger enables you to trigger on anything you can see in your capture. So a lot of flexibility and power. Another way to look at this is, it doesn't require a very large voltage swing. So I'm triggering on these small rising edges of this sine wave that's riding on the bigger sine wave. You see that the signal is consistently and cleanly triggering right there. So a lot of power, and you can alternatively turn up the hysteresis. So if you had a noisy signal and you didn't want the digital trigger to wiggle on a noisy signal, you could turn up the hysteresis and ignore the noise. So you have flexibility both ways. Perfect. So superior spectrum, what are we talking about here? And why should your scope have superior spectrum? Well, what is using an FFT on a scope? It's basically using a scope for spectrum analysis. And you enjoy a few benefits of having an FFT on a scope. Every one of the channels is now an RF channel. It's inherently synchronized between time and frequency. You have a wideband capture. You can use time gating in the time domain to isolate what in the time domain has frequency domain components, and that helps you find the causal effects. And but the quality and the speed of the measurement relies on a few things. It relies on a good ADC with low noise and a low noise front end. How quickly you can process the FFT. This is a signal processing intensive algorithm. So if you can do this in hardware, that's even better instead of doing it in software, because you can speed things up. And you want signal analyzer like setups. So you don't want to have to fumble with time base to get an FFT to work. So what are some applications for an FFT? You might want to look at rapidly changing signals. You might want to understand if there's any noise riding on your time domain trace. It might look like a flat line with just some noise, but the FFT will help you find frequency components of that, even very small frequency components like this one. An FFT will also help you identify hidden signals. And you could look at things like clocks. In the time domain, it's not obvious if a clock is clean or not clean. In this case, the FFT shows the clock looks clean. And in this second case, the FFT shows that there's sidebands, but the time domain still looks identical to the previous one. So an FFT can be a quite powerful debug tool. So let's take a look at a demo of the superior spectrum of the MXO. Okay, first thing I want to point out about the spectrum is the update rate. I think I'm currently, let me see how quickly I'm currently showing FFTs. So this is 500, 400, 500 FFTs per second. Most scopes in this 4000 or 4 series class are only going to show up to 10 FFTs per second. So this is already dramatically faster than anything in its class. But even at 500 FFTs per second, you can see that that signal is walking across, but I know that the behavior of this signal is more dynamic than this. And I'm going to remove that restriction, and you can see that the signal is in fact FM modulated, and the FFT is able to keep up with that signal behavior. And so this is dramatic step improvement into what's been available in the 4000 class oscilloscope family. So you can really see the behavior of the dynamic nature of signals. Another way that FFTs are commonly used on 4000 class scopes is EMI debug. And okay, here I'm just using a square wave as a representative signal. But imagine we're doing EMI debug here. We've got a nice table of peak values. So that's very handy. And you can do things like turning on a peak list right on the waveform. So those are really handy as you're moving a near-field probe around the board. And imagine having the ability to have the FFT update 45,000 times per second. You're going to be able to move the near-field probe around rapidly and still capture events as you move around. It's going to be able to keep pace with your movements. You're going to be able to capture spurious events, etc. So really powerful for lively, and dynamic spectrum analysis use cases. Awesome. So the last thing we want to talk about is smart grid, and this is a user interface topic. And we find that customers really appreciate the Rohde-Schwarz user interface, but we're talking about it last because you have to see all those other benefits in your lab. You have to understand that it's going to affect positively impact your measurements, the time you spend collecting measurements, etc. A lot of benefits there, but the user interface, actually, a ton of benefits here. What are they? Well, first of all, we have a very large touch screen, and a majority of the screen is used for waveform. When you are going to adjust things, we have a box design. So even if you touch, off center in these various areas because of the box design, you're still going to activate what you're trying to activate. The cursors are dynamic. They show values dynamically. And if you're wondering, okay, well, where do I find something? That menu's in German, but typically, of course, it's localized to English or your language of choice. But that would say search. And if you wanted to, for example, change the color of the waveform from yellow to pink, but you didn't know where to find that, you could simply type in something like color, and it'll lead you right to that menu. So that's one thing about the GUI. Another way of thinking about this, and here you can see there's a really huge space for waveform viewing, is to have a toolbar that's handy and configurable. And also the most important settings, like the trigger setting, horizontal and acquisition settings. You want to be able to see those, but also just simply touch on those boxes and make changes to the setup. Find all your channels, logic, math, buses, reference signals, spectrum, generator settings, etc. It's all right there at the bottom, as well as the menu. And how do you turn on a signal? You can just touch on one of the icons. It moves it over to the bottom left, and it shows you its settings. So in that case, it's 25 millivolts per division, 500 megahertz, DC 50 ohms, and 0 volts offset. So all of those are right there at a glance. And the other cool thing is, let's say you want to reposition waveforms to better understand or organize your thoughts. It's as simple as dragging and dropping them where you want them on the display. So that's the Smart Grid. Let's take a look at Smart Grid. Cool. So here we have two different signals, channel 1, channel 3, and we also have a math trace. And right now they're all on top of each other, and sometimes we just do things like move things around and change the size of signals and move them all around on one grid, but this is still a little bit crowded, and it's also not utilizing all the bits of the ADC if you do that. So you don't want to decrease the signals because you don't take advantage of the ADC and the dynamic range of your scope. Instead, with the Rohde-Schwarz Smart Grid, you can grab one of these icons and put it wherever you want on the screen and move it. So let's say we wanted to put them next to each other instead of above and below. There's a trash can there. I can get rid of that extra grid. And now we've got these waveforms next to each other. If instead I'd like M1 to be under channel 1, I can drag it and drop it there. So Smart Grid enables you to move things around and organize your desktop in a way that makes sense for the task at hand. The Smart Grid that I talked about earlier is along the top. And so that's where I have things like zoom that I use often. If you touch zoom, you can draw a box, create a waveform, and it's right there. So the toolbar is really nice because you can decide what you display and in what order you display those tools. So it's as simple as highlighting these or unhighlighting them. I'm going to take a few of them off. And even if you want to find out what they mean, have a nice little video talk about what they are. The toolbar is a nice way to access your most frequently used applications. And then you can touch on things like the trigger menu to bring you right up to the trigger settings, or acquisition to bring you right up to acquisition. So that's Rohde-Schwarz Smart Grid. What oscilloscope have I been using for today's demo? This is Rohde-Schwarz's newest oscilloscope called the MX-04. And it has some really cool industry firsts. 4.5 million waveforms per second, 12-bit ADC that goes up to 18 bits in HD mode, 400 megapoints of memory per channel, and a digital trigger system, as well as a 2-channel ARB, and it's MSO ready. All this starting at $8,500. So I just wanted to point out the scope I was using there and want to thank you, and we'll move on to the questions and answers.